Welcome to this special edition of Frequency Matters, the RF and Microwave Update. I'm Pat Hindle, here with my co-host Gary Lerude, and we have a special guest today, Alastair Upton, Senior Vice President of Business Development at Anokiwave. Welcome.
Thank you. Good to be here.
So Anokiwave has been on the show a few times now, talking about 5G millimeter wave technology and how your ICs are enabling that. Can you tell us what you're seeing in the market today in 5G and what progress Anokiwave is making?
These are exciting times. 5G has arrived, and I think as a consequence of that, we're going to see the largest volume of millimeter wave ICs ever produced. So why do I say 5G has arrived? So Verizon announced their fixed wireless access service,
right.
And it's early days yet, but anecdotally it seems to be going really well. AT&T just announced a 5G browsing session with 3GPP compliant equipment, so that's the network infrastructure together with the CPE. So that tells us that they're getting ready, and they've announced that they'll provide 5G service to a number of cities in this year and a total of 19 cities in 2019. Also, T-Mobile has announced some agreements with some OEMs, and that tells us that they're getting ready as well. So in the US market, the network operators are predominantly using the high band, which is the millimeter wave spectrum. And that's where you can get the widest bandwidth and the highest data rates. And it's traditionally been 39 gigahertz, 28 gigahertz, and there's even more spectrum coming. In fact, fairly soon there'll be some auctions for even more 28 gigahertz and quite interestingly some 24 gigahertz spectrum. And we believe even more spectrum will be allocated next year. So we really do see an acceleration in the millimeter wave area. As the market leader in silicon ICs for the 5G antennas, we continuously to aggressively solve the key technical problems. Our second generation 3GPP compliant ICs are available now, and our third generation are in advanced development. As the 5G rolls out, we continue to see additional applications. It's not only the high power base stations, but it's the fixed wireless access. There's things called integrated access and backhaul, small cells, or these radio access points, all the way through to the laptop and mobile devices. So we just see a proliferation of new applications coming. That all sounds great, but as we're starting this journey, we're going to continuously see technical and economic factors being solved, and so we're focused on solving those and helping our customers get better performance and improve the costs. Just to give you an example, we're focused on improving the transmit power efficiency of these antennas. It's one of the key parameters. It affects everything. It affects the size of the antenna, the cost of the antenna, the weight of the antenna. Managing the heat is really critical.
Right.
So we're focused on a key performance indicator, which is called the consumption factor. This is a factor that was first looked at by NYU, and it maximizes the total radiated power, EIRP in watts, divided by the power dissipation in watts. And it's for the total transmit channel. So we're improving the PA, we're improving the rest of the beamforming IC, all of the ICs, and in fact, right now we're looking at the total transmit chain, including the DACs, the digital to analog converters, to maximize this ratio of EIRP to power dissipation. That's one of the key factors that we're working on. We also have a few other factors in our RICs, zero cal to help with the calibration, as well as some green functions.
You mentioned zero cal. Tell us a little bit about the context for what's required to calibrate a phased array and why this is a benefit to the operators.
Yeah, so let's consider why traditional phased array antennas need calibration. So the way that a phased array works, it uses the relative phase between each of the elements, and we also use the amplitude to vary the power level as well as to do some amplitude tapering. In the real world, the manufacturing RF tolerances of the components and the beamforming networks means that there's too much variation, so you have to calibrate. And this calibration can be a really time-consuming thing because you have to isolate each individual element. So if you cast our minds back to 25 or 30 years ago, this could take several hours, even weeks, to calibrate some large arrays. So anything that we can do to minimize or even eliminate the need for calibration is a really good thing. So the Zero Cal is an Anokiwave proprietary. It's a patented IP. It's where we use some on-chip programming to basically counteract these variances, so that when we deliver the chips to our customers, they don't need the calibration. Where this manifests itself is really in the side lobe levels of the antenna. So, for example, if we apply an 18 dB taper to the array, typically what you would see without Zero Cal is about a 9 dB side lobe level, which is pretty high. By applying the Zero Cal IP inside the chip, we're able to reduce that to 19 dB side lobe levels.
Wow.
So it's a pretty dramatic improvement. So we think this is going to minimize and in a lot of cases eliminate the need to do calibration. And this is a really key thing for our customers. In fact, we have some nice testimonials from several customers, some from the commercial space, some from the traditional aerospace and defense world as well, where they've said that these are some of the first times that they've put antennas together without needing to calibrate these. So we think that's going to just help the overall throughput of the number of antennas you can produce and the cost of testing these devices.
Impressive.
So you've been speaking about how there's a great need to reduce the power consumption of 5G infrastructure and how your arrays support the green operation. Can you tell us what improvements you made on the IC level and how you implemented those to accomplish that?
Yeah, so as I mentioned, the whole total energy is a key factor. It's not only the size and the cost and the weight that I mentioned, but if we look at the network operators, their OpEx costs, the energy is a significant portion of that. In fact, recently we did a calculation that if you take a typical network, just the RF antenna electronics alone could consume 2.65 terawatt hours annually of energy. Wow. That's a big number. In fact, it's 63% of the output of the Hoover Dam.
Wow.
And anything that we can do to reduce that. So because we use silicon in our ICs, we're able to take advantage of the CMOS to do a significant portion of the chip is a digital core. So we have digital functionality in the chip. So what we are able to do is to do certain functions. We can do fast beam steering with that digital core. We can do some on-chip telemetry. But one of the things that we do is what we call the greens function. So we're able to turn off the ICs throughout the antenna. So just to give you an example how this could be used, if you're looking for a far user, you need all the power, you need all the antenna elements turned on. If you're in a near user situation, you don't need all that power, and you can turn off portions of the antenna, and you can save a lot of power by doing that. And we can do this dynamically. We can do this on a symbol by symbol basis, so less than 300 nanoseconds. So this is a really dynamic way to reduce the average power consumption. And in fact, that 2.65 terawatt hours numbers, we feel like using the greens functionality, we can reduce the overall power consumption by 33% by using this feature.
Wow.
And this is it's good for the operators, and it's just good for being green.
Oh, absolutely. So we saw recently an announcement you made that you had joined the Open RAN Alliance, ORAN.
Yeah.
What is the purpose of that group, and what are the benefits and the contributions you expect to make being part of it?
It's just getting started. It's an initiative to open up some of the interfaces in the radio access network. So as the 5G gets implemented, there's going to be a lot more devices at the edge of the network, so having some common interfaces does make sense there. So how we got into this is that we have been supplying some of our innovators kits, the 64 element, the 256 element innovators kits to some of the network operators, and they've been using those in their labs and for doing various tests. So we were invited by a couple of the leading network operators to participate in ORAN, and specifically into Working Group 7, which is the realization of white box hardware. So we're going to be supplying the chips to go into the arrays, and we're also going to be helping with specifying the device specifications for mmWaves. We're a little bit removed from the main open interface. At first we thought the interface may be between the antenna array unit and some of the other electronics, but it's really going to be at the fiber interface or the eCPRI interface. So we're a little bit further removed. So our contribution is going to be mainly on the array side and helping with the mmWave end of that alliance.
Given the amount of innovation that's taking place, it seems like an alliance like that to define some standards and some interoperability is a good move.
Yeah, I think it's supported by pretty much all of the major tier 1 network operators globally. So I think you're just going to hear more and more. And I think there's, expect to see more demonstrations at Mobile World Congress and other events on ORAN.
Exciting times.
It is indeed.
Well, we appreciate you coming by and giving us an update from Anokiwave and also your view of the market. I think the coming year is going to be, as you said, exciting times.
Very good. Thank you. I
you.
look forward to coming back and telling you about all the high volume of mmWave ICs the industry is producing next year.
Perfect.
Great.